Solving the Plastic Problem, Improving PETase for Real-World Environments by me, Kian. Background research. What are proteins and amino acids? Proteins are large biomolecules and macromolecules that have monomers called amino acids that perform different functions in enzymes such as PETase. There are three main amino acids in PETase. They are serine, aspartic acid, and histidine. There are 20 different amino acids in total, and they combine and alternate to create different protein sequences. The problem with recycling is that we actually only recycle 9.8% of plastics, and 90.2% of plastics are newly made. Another problem with recycling is that the quality and durability of the plastic decreases every time you recycle plastic. And eventually it will end up in the landfill anyway. What is PETase? PETase is an enzyme discovered in 2016 near a Japanese PET recycling site. PETase can degrade PET and convert it back to its basic form within 24 hours to 4 weeks, depending on the plastic's density, thickness, quantity, and also how many enzymes there are. How PETase works. So PETase works by when you put PET and PETase together in water, and it breaks the PET's ester bonds at a molecular level, turns it into mafette, and then PETase degrades the mafette into its basic form, which is terephthalic acid and ethylene glycol. The problem with PETase is that it cannot withstand enough pH to work outside and in different conditions other than labs. It is too costly and takes lots of expensive stuff to manufacture at a large scale. Too slow because the wild type degrades 0.25 mm film in 20 days, and it can only resist 46 degrees Celsius, and you need to heat the plastic up to 80 to 90 degrees to soften it so that the PETase can degrade it easily. New versions of PETase. These are some new versions of PETase that scientists have made. This one, the LLC ICCG-CO9, is the current gold standard and is 600 times faster than the wild type, resists up to 97.1 degrees Celsius, and has an optimal pH of 7.5 to 9.5. Fast PETase, which is 5 times faster than the wild type, survives 67 degrees Celsius and resists a pH of 6.5 to 9.5. Durapedase, which is 300 times faster than the wild type, resists up to 77 degrees Celsius and resists a pH of 8 to 9. My research question is, what specific amino acids are needed to create a PETase mutant with heat resistance, pH tolerance, and fast enough for large-scale plastic decomposition? And how can it be improved? My hypothesis is if I genetically edit PETase by combining most of the mutations from fast PETase, durapedase, as well as LLC-ICCG-CO9 into one PETase, then it can theoretically be able to decompose PET plastic 600 times faster, survive temperatures up to 149.1 degrees Celsius, and handle a pH level of 6 to 10.5. This is because fast PETase and durapedase and LLC-ICCG-CO9 each provide their own mutations to help with heat resistance, pH stability, speed boosts. And putting them all together fixes the three main weaknesses of PETase. So my research overview, I will talk about these three enzymes that degrade plastics and are made by scientists and their mutations. So the LLC-ICCG, which is the non-mutant gold standard, its map is very different from normal PETase, and it was made with silica protein, and the amino acids in it are very different. And the mutant LLC-ICCG-CO9 is 2 times more efficient than the non-mutant, and has 3 more amino acid changes. These are the amino acid changes for the non-mutant. And adding on to the non-mutant, these are the amino acid mutations for the mutant, which make it better from the non-mutant. So we cannot use some of the mutations later on when we're creating a better PETase because these two do not work in the normal PETase types and only work in the LLC type. And we could use this mutation N233C instead. and we cannot use F243I either because there is no alpha-9 at position 243. Instead, we have to use W159H. Fast PETase is 5 times faster than the wild type. It's 20 when the wild type takes 20 days to degrade the same 0.25 mm plastic sheet, the fast PETase takes 4 days. But it's nothing compared to the 500 years natural degradation time, which is very long. It was made in the University of Texas by AI. These are the mutations of fast PETase, and they help with different things. These are the other mutations of durapedase. So this is my new PETase. It's called Trident PETase. It uses all the mutations from all of these three different and these are the mutations for speed in Trident PETase. These are for heat. These are for surface binding. And these are for charge optimization, also for speed and stability. So my analysis, how I figured out the how much my be able to how much heat it can withstand, how fast it will go, and how much pH it withstand. So how I found out that my Trident PETase can withstand 600 times faster than the wild type is fast PETase as a 5 times boost with its mutations, Dura PETase as a 60 times boost, and LLC ICCG CO9 as a 2 times boost, making the grand total 600 times boost. So how I found out how much heat it can resist. So the wild type is 46, LLC adds this much, and Dura adds 31, making the grand total 149.1 degrees Celsius. Now you do not have to use this heat, so you have to heat the PET up to 149.1 degrees Celsius, but it is just a buffer, just in case, and it can withstand the 80 to 90 degrees that the plastic has to be softened to. The pH range. So how I figured the 6.0 to 10.0 is fast PETase adds 2.0, CICCGCO9 adds 1.5, and Dura PETase adds 0, making the grand total adding 3.5 points, which when you add to this makes it 6.0 to 10.5. The compatibility analysis. So, like we talked about in the LLC mutation section, these ones won't work for the PETase. Normal type PETase only works for the LLC, so we're gonna use these. So why I chose the name Trident PETase because a trident has 3 prongs on top of it, and I'm fixing the 3 main weaknesses of the PETase. Conclusion. Research and my math show that my hypothesis was right because my version of PETase and Trident PETase is the 3 main things that stop us from using enzymes outside of the lab. By putting them together, the best mutations from all 3 fast PETase, Dura PETase, and LLC-CO9, we can theoretically survive a heat of 149.1 degrees Celsius and a pH range of 6.0 to 10.0. Because these mutations help each other, the speed multiplies and 6 times faster than a wild type. This means that we can break down plastic in just a few days instead of waiting hundreds of years. Real world application. We can use this in Calgary landfills and degradation centers because it can withstand enough to work outside and heat. And we can use it for large scale recycling because it can withstand enough heat and can be softened and then degraded. And it will help us reach a point where there will be less pollution, plastic pollution in the world, and we'll not have to wait 500 years for the plastic to be degraded. Future directions. So, maybe I will use machine learning to find out how it will survive in different weather conditions. I can also verify this by making the Trident PETase in a lab and verify my calculations. And I can with a different researcher and check my math and my calculations. And can be used in large scale degradation. It can help us get rid of the plastic and solve the plastic problem. Also, I have used AlphaFold to make all the models of different PETases, including Trident PETase. And I have used the protein data bank to find sequences of the PETase and use them to make the models. Thank you, guys.